Welcome, curious minds, to another deep dive. Today, we're plunging into one of the universe's most profound and, well, inescapable truths. It's a principle so fundamental it governs everything, from, the quiet cooling of your coffee
Yeah.
to the explosive birth of stars and even the ultimate far distant fate of, well, everything. Have you ever stopped to really think about it? Why can't a shattered teacup just spontaneously reassemble itself on the kitchen floor, defying gravity and logic?
Right. It never happens.
Never. Or why do you never, not once, see smoke gracefully coil back into a candle flame, like you're rewinding a movie?
Yeah, like time running backwards.
Exactly. We constantly see things break apart, degrade, get messier, lose their structure, but the reverse. Never spontaneously. It's such a basic observation, almost too obvious to even question sometimes.
Uh-huh. It's just the way things are.
Now, take that idea, that undeniable principle, and stretch your mind out, way out, to an astronomical scale. Imagine just for a second that the universe stopped expanding. Maybe it even starts contracting, folding back in on itself.
Okay. A big crunch scenario, perhaps.
Right. Would it then not just rewind perfectly, like a film played in reverse? Would it go back to that initial super-ordered state?
Mm.
Maybe even set up another Big Bang?
Or would it be
Yeah.
messier?
Or would it be something completely different, something far more chaotic? Why isn't that perfect cosmic rewind possible? What's stopping it?
That's the key question, isn't it?
These aren't just idle thoughts, I promise you. They point to a central mystery, a kind of silent, pervasive force dictating the flow of events. It shapes our perception of time, the very fabric of reality itself.
It really does.
The answer, dear listener, lies hidden in one of the universe's most rigorously tested and fundamental laws. It's a principle so powerful it influences cosmic structure, governs life, and might even be the ultimate architect of the end of time. For this deep dive, we're talking about entropy. We're going to unpack this, explore how it explains that one-way street we call the arrow of time. And we're pulling insights directly from today's source material, entropy, the universe's inevitable journey to disorder.
Precisely. Our mission today is to really dig into entropy. Not just define it, but peel back its layers. We'll start with those simple, relatable examples you mentioned. The teacup, the messy room, and then expand outwards to its huge cosmic implications. We want to help you grasp the profound why behind so many things.
Okay.
Our goal for you, the listener, is to get a clearer, deeper understanding of why things unfold the way they do. From, like you said, your room getting messy to the far distant, almost unimaginable future of the entire cosmos.
Right.
This isn't just about learning a scientific term. It's about grasping a core truth about reality, how it shapes everything around us and within us, often in really surprising ways. It's like this cosmic undercurrent influencing every single moment.
All right, let's unpack this, maybe with a relatable thought experiment. One I think many of us know all too well. Imagine your room, just picture it. Impeccably tidy, books on shelves, clothes folded, desk clear, everything in its place, picture perfect order.
Okay, got it. A rare state for some of us.
Indeed. Now, how much effort, how much energy does it take to make that room messy?
Basically none.
Almost none, right.
Right.
Toss a few things around, kick something under the bed, pull clothes out of the drawer. Boom. Instant chaos.
Effortless disorder.
Shockingly easy. But now think about the reverse. How much work, how much sheer effort, how much concentrated energy and, intention does it take to get that room back to perfectly tidy?
Oh, way more. Significantly more.
Definitely. You have to pick things up, sort them, fold them, carry them, put them back in specific places.
It requires deliberate action, a plan, energy.
Exactly. A deliberate application of energy, a very specific sequence of actions to get back to that ordered state. You can't just wish it tidy.
If only.
This simple, everyday observation, believe it or not, is the most basic way to understand entropy. Fundamentally, people often call it a measure of disorder, but that's a bit simplistic.
Right, it's more nuanced than just messiness.
Yeah. More accurately, as our source points out, it's about the spread and dispersion of energy. Or you could think of it as the number of possible ways things can be arranged microscopically for a given overall state.
Okay, so more ways to be messy than tidy.
Exactly. A tidy room is low entropy because there's a very specific ordered arrangement, only one or maybe a few ways for it to be truly tidy. A messy room, though, high entropy. There are countless, almost infinite ways for things to be scattered around.
So the disordered state is just far more probable Statistically much more likely.
Precisely. It's easier to achieve that messy state. And this isn't just about messy rooms. It's why perpetual motion machines don't work.
Oh, right, because any process loses some energy.
Yeah. Every single process charging your phone, a star burning, inevitably generates some waste heat. It moves energy towards a state where it's more spread out, less useful.
Taking us closer to a state where no more useful work can be done.
Exactly. A state of maximum entropy.
And this seemingly simple idea, this tendency we see everywhere, it's the foundation of one of the absolute pillars of science, the second law of thermodynamics.
Right. That's the big one.
It really is.
Yeah.
It's not just a theory. It's considered a fundamental, unyielding truth about how the universe works, tested again and again.
Yeah.
And what it states is profound. In any closed system, and critically, this includes the universe as a whole, entropy always increases. Or, at best, it stays the same.
It never goes down on its own.
Never spontaneously decreases.
Okay.
This means things inherently move from order to disorder. Energy naturally spreads out.
Yeah.
It goes from being concentrated and usable
Yeah.
to being more spread out, uniform, and ultimately less usable. Think heat spreading out until everything's the same temperature.
And you see this constantly, right? Even if you don't call it entropy.
Absolutely. It's why your hot coffee cools down. It never spontaneously reheats itself unless you put it in the microwave.
Yeah.
Add energy.
Right. Or why iron rusts. Breaking down from structured metal to flakes.
Exactly. Or why anything complex, a car, a building, even us, degrades over time, unless we actively put energy into maintaining it, repairing it, eating food.
Keeping the order going.
Keeping the order going, yeah.
Yeah.
The universe has this built-in tendency towards disorganization, towards equilibrium, a relentless march towards a state where everything is just uniformly spread out. No more energy differences to drive change. It's a constant, one-way journey.
Which brings us right back to that shattered glass, doesn't it? The one that won't reassemble itself. We touched on it, but let's really dig into why it feels so irreversible through the lens of entropy.
Okay.
So when the glass shatters, the energy stored in its structure, the chemical bonds holding it together in that specific way gets dispersed.
Into all those little shards flying off.
Right. But it's not just the glass pieces. Energy also spreads out as the sound of the crash.
Sound waves carry energy.
And as heat. From the impact, the friction,
Yeah.
all that dispersal, breaking specific bonds into countless scattered fragments and spreading energy around, that significantly increases the system's entropy.
The order of the whole glass is lost, replaced by the much more probable disorder of shards and dispersed energy. Makes sense.
So the reason you never see the shards leaping up, magically fitting back together, is because it would require an event of just mind-boggling improbability.
Statistically impossible, essentially.
Pretty much. Think about it. There's only one, maybe a few ways for the teacup to be whole, but there are trillions upon trillions of ways for it to be shattered pieces on the floor.
Right. Many more ways to be broken.
For it to reassemble, every single molecule, every shard, moving randomly, would need to suddenly perfectly reverse its path, coordinate with impossible precision.
And clump back together into the exact original shape.
Exactly, while also sucking all the sound and heat energy back in from the surroundings.
Which would be a massive decrease in entropy.
A huge decrease, and that would directly violate the second law of thermodynamics. It's not just unlikely, it's basically forbidden by the fundamental rules of physics.
It's just not how the universe works, period.
That's such a powerful illustration, and it leads straight to this profound consequence. This constant, irreversible increase in entropy is exactly why time seems to move in only one direction.
Yes, this is what we mean by the arrow of time.
The arrow always pointing forward.
Always forward. The past, by definition, is a state of lower entropy. Every moment that passes, every event that happens, entropy ticks up, irreversibly. The universe is constantly moving from a more ordered, less probable state to a more disordered, more probable one.
Like shuffling a deck of cards. Easy to go from ordered suits to random.
But almost impossible to get back to the original order just by random shuffling.
Yeah.
Time is like the unfolding of that cosmic shuffling process.
And this connects deeply to our own experience, right? Even memory.
Absolutely. Even our brains, our memories. They're physical records of a universe that was in a more ordered state before the memory was formed. Making a memory involves physical changes in the brain, neurons firing, connections strengthening. These are processes that themselves increase entropy locally, releasing heat.
So we remember the past because it's the lower entropy state that has already unfolded into the present.
Exactly. You can't remember the future because that higher entropy state hasn't happened yet. It doesn't exist as a recorded configuration that is past.
Wow.
It really makes you think, doesn't it? How does this fundamental law shape not just physics, but our very perception of time, our ability to remember, what it even means to experience life sequentially.
It suggests our subjective feeling of time flowing forward is tied directly to this cosmic arrow of increasing entropy.
Inextricably linked, always pointing forward, never back.
Okay, let's pivot now to a really big one. A huge cosmic paradox that seems almost to contradict everything we've just said about entropy always increasing. The Big Bang, the very
Right.
start, unimaginably compressed, dense, super hot, tiny, packed with all the energy and matter.
The primordial fireball.
Right, intuitively you'd think.
Yeah.
Super hot, super compressed, dense. That must be incredibly chaotic, right? Extremely high entropy.
It seems like it should be maximum disorder, a hot mess.
But I know some physicists, Roger Penrose is maybe the most famous, argue something almost opposite, that the early universe was somehow remarkably ordered.
Yes, that's a fantastic point, and it gets right to the heart of one of the biggest puzzles in cosmology.
How does that work? How can something so hot and dense be ordered?
Well, Penrose's idea, his Weyl curvature hypothesis, tries to explain this. He suggests that while the matter and radiation in the early universe were indeed incredibly hot and sort of chaotic high thermal entropy.
Okay, like a hot gas.
Exactly. The gravitational field itself was astonishingly smooth and uniform. This is the key. Entropy isn't just about heat and particles. It's also about the structure of spacetime, the gravitational field.
Ah, so gravity had low entropy.
Incredibly low gravitational entropy. Think of it this way. If gravity had been chaotic and clumpy right from the start, it would have immediately collapsed everything into black holes everywhere.
Preventing the smooth expansion we needed.
Precisely. It would have prevented the large-scale structures, galaxies, stars, planets from forming over billions of years as the universe expanded and cooled. That initial gravitational smoothness represented immense potential order.
So the order was in the smoothness of gravity itself, not the hot matter.
That's the core idea. The matter was hot and messy, but the stage it was playing on the gravitational field was incredibly flat and uniform.
Wow. Okay, so the puzzle then is why? Why did the universe begin in that state, so exquisitely ordered gravitationally?
Exactly. That is the profound mystery. If the natural tendency is for things to go from order to disorder, why did the universe start in such a highly ordered condition? It seems backward.
It flies in the face of the second law's directionality.
It does at first glance. This isn't just a little curiosity. It's what drives scientists to ask what happened before the Big Bang, or does before even make sense.
Right, maybe time itself began then?
Perhaps. It forces us to think about the fundamental nature of reality. What does it imply if the very beginning of everything had this extraordinary level of built-in order in its gravitational fabric?
It's a question cosmologists are still wrestling with. Multiverse ideas, quantum gravity.
All trying to explain that initial, improbable low-entropy state. It's a huge driver of theoretical physics.
Okay, let's bring it back down to Earth a bit. Still paradoxical, though. Maybe even more relatable. If the universe is always marching towards disorder, what about life? What about us?
The life question always comes up.
Right. A human body is just an astonishing example of intricate order, complexity, highly organized structure. We fight decay constantly.
We build things too.
And we build things.
Right.
Cities, infrastructure, complex systems. We write books, create art symphonies, sculptures, all demanding incredible organization, precision, acts that create order locally.
Reducing local disorder, yeah.
Doesn't that seem like we're fighting entropy, pushing back against the universal trend? How can life even exist, let alone build complex things, if the universe is inherently getting messier?
It feels really counterintuitive, doesn't it? Especially when we think about evolution building complexity over time.
Totally.
But here's the crucial clarification, the part that often gets missed. Life isn't actually an exception to the second law.
It's not.
No. Life represents local and temporary pockets of order. But, and this is the key, creating and maintaining that local order comes at a significant entropic cost to the wider universe.
Ah, okay. Like tidying your room. The room gets ordered, but you expend energy, create heat, maybe sweat a bit,
Right.
increasing disorder elsewhere.
Exactly that principle.
Yeah.
Scaled up. To build and maintain our complex bodies, our cities, our art, we have to consume energy and release waste. We take in low entropy energy, concentrated energy, like sunlight for plants, or the chemical energy in food for us.
Ordered energy sources.
Right. And through metabolism, activity, building things, we convert some of that into useful work to maintain our order, but a lot of it gets released as high entropy energy, mostly waste heat.
So every breath, every meal, every action releases heat into the environment.
Every single one. That heat is dispersed energy, less usable, higher entropy. We are constantly taking organized energy and converting it into disorganized energy, increasing the overall entropy of our surroundings
So we're creating little islands of order.
by making the ocean of disorder around us even greater.
Wow. Our source even calls life entropy's most ingenious trick for speeding itself up.
It's a provocative way to put it, but yeah. Essentially, complex systems like life are very efficient at taking low-entropy energy and degrading it into high-entropy heat, thereby accelerating the overall increase of entropy in the universe.
So we're not defying entropy, we're actually facilitating it, accelerating it.
In a way, yes, while creating these temporary, beautiful, complex, but ultimately fleeting pockets of local order. It is. Think about it. Every act of living, from eating breakfast to just thinking, contributes to this larger cosmic trend of increasing disorder. Even as we personally strive for order in our lives, we're part of the flow.
Part of the inevitable journey to disorder. Okay, from life, let's jump to the truly cosmic extremes. Black holes.
The ultimate entropy engines, as they're now called.
Right, but initially, they were a real puzzle for entropy, weren't they?
They were a huge problem. For a while, the thinking was maybe they had no entropy.
Why? Because they seem so simple from the outside.
Exactly. The no-hair theorem says a black hole is just defined by mass, spin, and charge. That's it. They seem to swallow everything complex stars information and to just become slightly heavier or spin faster. Very simple objects.
Like the ultimate cosmic data shredders.
Pretty much. But that created a massive paradox for the second law.
The law that says entropy must always increase.
Right. If black holes had zero entropy, what happens if you throw something with high entropy, like a whole star, a messy, complex system, into one?
The star's entropy vanishes behind the event horizon.
And if the black hole has no entropy itself, then the total entropy outside the black hole seems to have decreased.
Which breaks the second law.
Exactly. A direct violation.
Oh.
It was a major theoretical crisis in the early 70s. Physics seemed broken.
So how is it resolved?
Well, enter Jacob Bekenstein. He thought deeply about this paradox and had this brilliant insight.
Which was?
To save the second law, black holes must have entropy. There was no other way. He proposed that the entropy must be related to the size of the black hole, specifically the area of its event horizon.
The point of no return. So bigger black hole, more entropy.
That was Bekenstein's idea. And then Stephen Hawking came along and did the heavy lifting mathematically.
The famous Hawking.
The very same. He proved, using quantum mechanics near the event horizon, that black holes do indeed have entropy. And not just a little bit, massive amounts of entropy. Directly proportional to the surface area of their event horizon, just as Bekenstein suspected.
So there are these huge reservoirs of entropy.
The ultimate entropy engines, yes. When they swallow matter, their event horizon grows, and their entropy increases, perfectly balancing the books for the second law. The order of the infalling stuff is converted into the black hole's entropy.
Okay, that saves the second law. Phew.
But Hawking went even further with Hawking radiation.
Right, the idea that black holes aren't actually completely black, they evaporate.
Exactly. It's a quantum effect near the horizon involving virtual particle pairs. One falls in, the other escapes, carrying energy away.
So the black hole slowly loses mass.
Slowly shrinks and evaporates over incredible timescales. And this radiation is thermal. It carries away the black hole's enormous entropy, spreading it back out into the universe.
Ensuring the total entropy continues to increase even as the black hole disappears?
Precisely. So even these cosmic giants, once thought to be simple endpoints, are active players in entropy's game. They gather it up, store it, and then slowly release it back, always driving the universe towards maximum disorder.
Always maintaining the balance. Okay, so we've looked at the start, at life, at black holes. What about the end? The universe's ultimate trajectory guided by entropy.
Where is it all heading?
Yeah. We know the universe is expanding, even accelerating, galaxies moving apart.
The current picture, yes. Driven by dark energy.
Now, for a long time, there was this other idea, right? The big crunch, gravity eventually wins, pulls everything back together.
A popular model, historically, yes. The universe collapses back into a point. A cosmic reset, almost.
Almost poetic, but from an entropy perspective.
That's where the poetry kind of falls apart. A contracting universe leading to a big crunch would absolutely not reverse entropy.
You wouldn't be a rewind.
Definitely not. It would be a neat playback of cosmic history in reverse, returning to that pristine, low-entropy, Big Bang state.
Why not? What would it actually be like?
A nightmare. Utter chaos. Instead of galaxies neatly reforming, stars unexploding. It would be a catastrophic collision. Everything stars, black holes, galaxies, gas clouds smashing together violently, gravitational fields becoming incredibly chaotic and lumpy.
Like a cosmic demolition derby.
Exactly. A destructive cascade generating immense heat, spreading energy out uniformly. It would be a state of complete, messy disorder. Very high entropy.
So even a contraction leads to more disorder, just a different kind.
Precisely. It reinforces how relentless entropy is. Even if the universe tries to turn back on itself, it can't undo the increase in entropy. It just finds a different, probably more violent path to maximum disorder.
Entropy always wins. No resets allowed.
No resets. It really makes you think about the fabric of existence, doesn't it? Even reversing the expansion leads to chaos, not order.
That is sobering. Okay, so if a big crunch is also a path to disorder, what's the most likely end game according to current science, given the accelerating expansion?
Right now, the leading scenario, the one detailed in our source, is what's called heat death.
Heat death. Sounds final.
It is the ultimate triumph of entropy. In this picture, the universe just keeps expanding forever, accelerating.
Pulling everything further and further apart.
Exactly. Over unimaginable timescales, trillions upon trillions of years, way longer than the universe's current age. Stars will all burn out, exhaust their fuel,
Need more light.
just fading embers radiating their last bits of energy into the void, getting ever more dilute. Black holes, the entropy engines, will slowly evaporate via Hawking radiation
Until even they are gone.
until even they are gone, leaving behind just a diffuse soup of fundamental particles and low-energy photons spread incredibly thinly across a vast, cold, dark expanse.
So everything just spreads out until it's uniform.
Perfectly uniform. No temperature differences, no energy gradients left anywhere, nothing to drive any process, nothing can happen.
A universe where nothing ever happens.
That's heat death, an endless, featureless, silent, incredibly cold void. Thermodynamic equilibrium, maximum entropy achieved. No more change possible.
Wow. Not a bang, but a whimper stretched out over eternity.
A quiet, eternal fade into unchanging uniformity.
Okay, so heat death is the front runner. But the source mentions other, maybe more dramatic possibilities.
Yes, there are other theoretical contenders, though perhaps less likely based on current data. One is the Big Rip.
That sounds violent.
Extremely. It's driven by a hypothetical type of dark energy, phantom energy, whose repulsive force grows stronger over time. The expansion would accelerate so uncontrollably that eventually its force would overcome gravity holding galaxies together.
Ripping galaxies apart.
Then solar systems. Then planets.
Yeah.
Then even the forces holding atoms together. Space-time itself tears everything apart.
Literally ripping the universe to shreds.
A very dramatic, explosive end.
And the other alternative mentioned, the big bounce.
Ah, the cyclical idea that maybe the universe doesn't end but bounces, a big crunch happens, but instead of a singularity, quantum gravity effects cause it to rebound into a new Big Bang, starting a new cycle.
An endless series of universes. That sounds more hopeful.
It does, but entropy throws a wrench in the works even there.
Oh, how so?
Even in big bounce models, it's generally thought that entropy would carry over or increase from one cycle to the next.
So each new universe starts off messier than the last one.
Exactly. It wouldn't be a perfect reset to that pristine low entropy state. Each bounce would likely start with higher overall entropy, less potential for complex structure, more diffuse energy.
Like a cosmic photocopier getting worse with each copy.
That's a decent analogy. It suggests that even a bouncing universe is still on this grand, irreversible journey towards maximum disorder over many cycles.
So the overarching theme remains.
Entropy is inescapable. Whether it's a slow fade to heat death, a violent big rip, or a series of messy bounces, the underlying trend is always towards increasing disorder. It's the fundamental arrow dictating the flow of cosmic time, pushing everything towards ultimate uniformity and equilibrium. It's the constant driver no matter the specific path.
And as entropy climbs relentlessly, what does that mean for all the amazing structures we see now? The galaxies, the nebulae, solar systems?
It means they are temporary. All the intricate, beautiful complexity, the spiral arms of galaxies, the glowing gas clouds, the stable planetary orbits, even life itself, it's all destined to be scattered and dissolved.
Unraveled by entropy.
Exactly. Stars will die, their energy radiating away into the cold void, becoming impossibly dilute.
Galaxies will drift apart or merge chaotically, their structure is eventually erased.
The ultimate outcome is that all this complexity collapses into uniformity. featureless equilibrium.
The source used that analogy of a stunning image on a screen.
Yes, devolving slowly, relentlessly into just static. All the patterns, the colors, the definition, just blurring into undifferentiated noise.
That's the fate of cosmic complexity, from structure to static.
It's the triumph of the most probable state.
Yeah.
Maximum disorder, where everything is smoothed out. It really makes you pause and reflect, doesn't it?
It does. How does it feel to contemplate that all this breathtaking beauty, billions of years in the making, is headed for such a simple, undifferentiated end?
It challenges our sense of permanence, our search for meaning and structure.
It really does, which leads to maybe the deepest question of all, that image of static, heat death, maximum entropy reached. If absolutely no more change can occur, because everything is uniform, no energy gradients, what happens to time itself?
Does time even exist if nothing changes?
Right. Our whole concept of time is tied to change. Clocks ticking, sun moving, us aging, stars burning, processes.
Ends unfolding?
But if all energy is uniform, no gradients, no processes possible, nothing to distinguish one moment from the next, does the cosmic clock just stop?
Is there a next moment if it's identical to the last, and nothing can happen to mark its passage?
Does time lose its meaning?
It's a profound philosophical question rooted in physics. Without change, without entropy having anywhere else to go, without energy flowing, does time itself cease to be relevant? Or cease to exist altogether?
An eternal, unchanging now.
Perhaps. A static void with no duration, because duration implies change.
So connecting the beginning and the end, if time arguably began with that incredibly low entropy state, allowing for change and evolution.
Maybe time ends when entropy reaches its maximum, when its work is done, and there are no more states to unfold into. Time could be seen as just the measure of entropy's journey.
Wow, that is genuinely mind-bending. Is time just a function of entropy? And when entropy maxes out, time dissolves.
Leaving just eternity, an unchanging void. It challenges everything we assume about existence.
And so we bring our deep dive full circle back to why that teacup doesn't fix itself.
It's the same fundamental reason the universe can't just rewind: entropy.
Exactly. Quietly, persistently guiding everything, micro to macro. But it's crucial to reframe it, isn't it? It's not just destruction or decay.
No, it's also the driver of creation in a way.
Right. It's behind star formation. Gravity creates order locally but releases huge amounts of heat, increasing overall entropy. It's behind life, creating complex structures by processing low entropy energy into high entropy waste.
It shapes cosmic history. Structures emerge, evolve, and dissolve, all under entropy's influence.
It really is, as the source suggests, the architect of the universe as we know it, the engine of all change.
Which leads to a final, maybe provocative thought for you, the listener. If this principle shapes everything, galaxies, life, memory, our own existence, then is it possible that the entire story of the universe is simply entropy telling itself?
The narrative thread from the Big Bang's order to heat, death, stillness.
The grand story of transformation towards equilibrium. Let that thought linger. Notice the subtle and not so subtle ways entropy plays out all around you.
Thanks for joining us for this deep dive into the heart of cosmic order and inevitable disorder.